Hello, my name is DeAndre Jones. Today we're going to talk about optimal controls. So first we're going to talk about the general overview and design philosophy of designing an optimal controller, then go over two examples of optimal control design, then go into more detail with one applied to the linear Newton system, and then talk about how optimal controls can be applied to the lambda control problem. So generally, optimization of controls encompasses the field of designing a controller that maximizes or minimizes a set of parameters. So what this means is you have a state trajectory that has your position, velocity, angle, whatever state variables you're trying to track. Then you want to take that and then apply a performance index to it. So the performance index lets you choose what you're trying to minimize. So your control input, your state, final state, or your intermediate state. So the way to do this is basic calculus. You form a function called a Hamiltonian, which is a function of the performance index in your original state. Then from here you can take derivatives to find critical points, which generally means a minimum maximum saddle point. And then you can use your boundary conditions, which is a function of your problem statement, to solve for the state and costate equations. So an LQR lets you do this, but for a system that develops dynamically in time with a quadratic cost function. So from here you have your cost function, use the algebraic Riccati equation to solve for a P matrix. Then from there you can get your Kalman gain, you get your control input, and then you can solve for your state. So for a problem where you have the fixed final state, the procedure is a little bit more complicated. So from here you have a cost function where S and Q are the weights for state and intermediate state, or for final state and intermediate state respectively. So they're generally 0 because the final state is known. So you want to minimize the input control. You go through this algorithm where you solve for your S, integrate it backwards, and plug it into your K, get your V, integrate it, get your P, integrate it, and then you put it into your U and you solve for your state. So if you're using MATLAB OD45, it gets a little bit tricky because OD45 can only integrate forward in time. So once you integrate it, you have to flip it the time index around with the variables. And we'll talk about that more in the example coming up. And then you have a version of this called the SDRE. So what this lets you apply the LQR technique for nonlinear systems. To do this, you usually take your nonlinear system, you factor it out, or you non-dimensionalize it, and then you make sure it's controllable through the controllability test, and you apply the same LQR method but at each time step. So basically, you're taking a nonlinear system and you're approximating it as a linear system, and then the more time steps you have, the more optimal it is, but also the more computing power it takes. So this is an example of fixed final state for LQR using Newton's law. So on the left here, you have the state space representation of the system. On the right here, you have the equations you're going to use. You have your performance index, your K, your S, and your V. You take this, and then you integrate it, flip it around, put it into your U, and integrate U in your state. One thing to note here is that the initial values for S and V are a function. Well, S is a function of C, your input, but V is a function of your reference, and your reference is a function of your final state. So basically, your R is equal to your final state. So here's an example of the data of the output MATLAB will give you. So once you integrate it and then you flip it around and then you plug it back at OD5, integrate the state forward, you can track how well it tracks the step response. So here is the X1 variable tracking the step response. And then you can get your V and your S trajectories, which notice that they taper off to one value. Then here's the example code of once you integrate it through OD45 and you flip it around. And here's the function you feed into OD45. Notice that it's just the S and the V functions that I've already described. You take them, OD45 integrates them, and then you need to run OD45 a second time for MATLAB because the first time creates a time step that you will need to match up with the X and U variables once you integrate those. So the interpolate function lets you do that. And then lastly, we're going to talk about the lambda control problem. So it's broken down into two phases. Phase 1 is a nonlinear system where you approach the landing site with tangential velocity. And then you zero yourself out, so you're straight up and down. So you start the phase 2, which is a linear system where you just descend to the surface. Here you can use polar coordinates to describe the system. So you have your negative velocity, angular velocity, etc. But for phase 2, you switch to a Cartesian system since it's just up and down. To linearize the system, you need to do something called non-dimensionalizing. So from here, you take the gravitational parameter of the moon, and then the radius of the moon. Then you use those to linearize the system and take all the units out. And then from here, you get your A, your B, your U matrices. Notice how S and Q are 0 because you're not minimizing the final state and the intermediate state, just the control input. And your final state is the initial state of phase 2, so you see in here. You're leveling off to 90 degrees, and your final velocity 0, but your final radius is still the radius of the moon plus 30 meters. Then here you run through the same algorithm described before, but for each time step. So you get your S, your P, your V, your U state. And then once you get to phase 2, you switch to a linear system where it's just you're twirling your vertical distance. And then you have your C, R matrix. Notice that the final velocity here is 0 since you're landing on the surface. And then, thank you for watching. So this video is created for my EC E6325 course. Thank you.